Welcome to Advanced Linear Algebra. Today, we are going to explore a beautiful and powerful concept known as the dual basis. If you have ever wondered how we can mathematically take a vector apart to see exactly what it is made of without solving tedious systems of equations, you are in the right place. Let us dive in. To understand the dual basis, imagine you are at a fruit market. Your basket of fruit is like a vector, and the specific fruits, like apples and bananas, are your basis vectors. Now imagine having magical barcode scanners, where one only counts apples and ignores bananas, and the other only counts bananas. In linear algebra, a linear functional is a mathematical machine that takes a vector and spits out a single number. The dual basis is exactly like those magical scanners, a set of specialized functionals perfectly tuned to measure just one specific building block while ignoring all others. Now that we understand the concept, let us look at its mathematical heart. This formula is the defining rule of the dual basis. The symbol f sub I represents our magical scanner, the ith linear functional. The symbol v sub j is the jth basis vector we are scanning. The symbol on the right is the Kronecker delta. It acts as a simple switch. If the subscripts I and j are exactly the same, the output is exactly 1. If they are different, the output is 0. If we change the functional to match a different vector, the switch activates for that new vector instead. Physically, this means the ith functional only detects the ith basis vector and is completely blind to the rest. Before we move on to other properties, let us see this defining rule in action with a concrete example. We will start with the simplest scenario, the standard two-dimensional plane. We are given the standard basis vectors e1 and e2, and we want to find the first dual functional, f1. We assume a general form, a times x plus b times y. We force it to obey the dual basis rule. It must output 1 when fed e1. Plugging in 1 for x and 0 for y, the b term disappears, and we immediately find that a equals 1. Continuing with our standard basis example, we must now apply the second part of the rule. We feed the second basis vector, e2, into our functional. Because the subscripts 1 and 2 do not match, the output must be 0. Substituting 0 for x and 1 for y leaves us with b equals 0. Replacing a and b in our original guess gives the final answer. f1 of xy equals x. This makes perfect intuitive sense. It simply extracts the horizontal coordinate. The final answer physically represents the exact horizontal length of any vector you measure. Now that we have solved a simple case, let us tackle a slightly harder, more realistic problem. Suppose we are using a skewed, non-standard basis with vectors 1, 2 and 3, 5. Extracting coordinates here is normally difficult. We use the exact same strategy, assuming f1 equals ax plus by. We enforce the rule that f1 acting on v1 must equal 1. This gives us an equation with two unknowns. We rearrange it to isolate a, giving us a equals 1 minus 2b. We will hold on to this relationship for the next step. Continuing our search for the dual basis, we apply the second rule. f1 acting on v2 must equal 0. This gives us 3a plus 5b equals 0. Now, we take our expression for a from the previous step and substitute it directly into this new equation. By doing this, we eliminate the variable a entirely, leaving a simple algebraic equation with only one unknown, b. We distribute the 3 into the parentheses, which gives us 3 minus 6b plus 5b equals 0. We are now very close to finding our functional. Let us finish solving for our functional. Combining the b terms gives 3 minus b equals 0, which means b is exactly 3. We plug this number back into our earlier equation for a, giving 1 minus 2 times 3, which results in negative 5. We have found both constants. Replacing a and b gives our final answer. f1 of xy equals negative 5x plus 3y. If you feed any vector into this magical scanner, it spits out exactly how many times you need to use the first skewed vector to build it. This is the physical meaning of our result. To truly understand what we just calculated, let us look at this visually. This diagram shows our skewed basis vectors, v1 and v2. The dashed lines are the contour lines of our dual functional, f1. Notice how the zero line runs exactly along the vector v2. This means no matter how far you travel in the v2 direction, the scanner registers absolutely nothing. It only registers a change when you move in the v1 direction, reaching exactly 1 at the tip of v1. The geometry perfectly matches our algebraic rule. Now that we know how to find a dual basis, let us explore why it is so incredibly useful. Normally, if you want to find the coordinates of a general vector, meaning the exact amounts of each basis vector used to build it, you have to solve a large, tedious system of linear equations. But the dual basis offers a shortcut. Because each functional in the dual basis is perfectly tuned to a single basis vector, we can use them to extract these coordinates instantly, bypassing the need to solve any equations at all. This saves massive amounts of time. This brings us to the ultimate payoff formula for the dual basis. This equation states that any vector v is equal to the sum of its basis vectors, where each basis vector is scaled by the number f sub I of v. In plain English, to rebuild a vector, you just use your dual basis scanners to measure exactly how much of each building block is present and then stack those building blocks together in those exact amounts. If the extracted coordinate increases, that specific building block becomes a larger part of the final vector. It is a perfect reconstruction. Now that we have seen this reconstruction formula, let us understand where it comes from by proving it. We start by writing a general vector v as a linear combination of our basis vectors, scaled by unknown coordinates c1 through cn. To find the first coordinate, c1, we feed this entire long expression into our first dual basis functional, f1. Because f1 is a linear functional, it respects addition and scaling. This means we can distribute the functional across every single term inside the parentheses, breaking a complex measurement down into a series of very simple ones. Continuing our derivation, we pull the constant coordinates out to the front of each functional. Now we apply our golden rule of the dual basis. We know that f1 acting on v1 equals exactly 1. We also know that f1 acting on v2, v3 and so on must equal 0 because the subscripts do not match. Therefore, every single term in this long equation vanishes into 0 except for the very first one. This gives us our final result. Applying f1 to the vector v instantly extracts the first coordinate c1. The proof is complete. So we have proven that the dual basis perfectly extracts coordinates. You might wonder why all of this matters in the real world. In quantum mechanics, the state of a particle is a vector, and measuring it requires a dual vector. The famous bra-ket notation invented by Paul Dirac is entirely built on this. The ket is the vector, and the bra is the dual basis functional. In engineering and computer graphics, when rotating a 3D model, the dual basis tells the computer exactly how to extract new coordinates instantly, saving massive amounts of processing power for every single pixel. Let us summarize what we have learned today. A dual basis is essentially a specialized set of mathematical measuring tools. For every vector in your basis, there is exactly one corresponding functional that measures it perfectly while ignoring all the others. This elegant pairing allows us to instantly extract coordinates, effectively separating the object itself from the tools we use to measure it. You have now covered the full topic. Mastering the dual basis is your key to understanding advanced transformations in both pure mathematics and applied physics. Great job today.